Most mathematical areas have concrete starting points, like integers in number theory, points and lines in geometry, and so on. But the area that we'll talk about today operates one level higher. It abstracts away the nature of the objects themselves and considers only how they interact. This extreme generality is what makes it the most abstract field of mathematics. With that said, abstract doesn't always mean difficult. In mathematics, abstraction is the process of stripping away all the details so that you can analyze the underlying structure, or the most essential ideas. The area that removes the most amount of details in order to study the pure core of the subject can be said to be one of the most abstract areas of mathematics. Category theory is powerful because it does precisely that. It reveals deep structural similarities between branches of mathematics that at first seem to be completely unrelated. I like to think in terms of analogies. Let's say you are walking into a massive library, but every book in this library is written in a different language and describes different worlds. One about numbers, another about shapes, a third concerns itself with logic, the fourth just focuses on infinity, and so on. Most mathematicians who study in this library spend their entire lives exploring just one of these books. But what about category theorists? Well, they are the ones observing from above. They don't care so much about what the books say, but they do care about how the books relate. They notice that something about how you multiply matrices is weirdly similar to how you compose functions, which somehow reflects how you glue topological spaces. And they ask the question, what if those similarities aren't just coincidences? What if they are clues of something deeper? That's category theory. It's a theory about relationships, and that's why it feels almost philosophical. In fact, it is often called the mathematics of mathematics. Its language is very abstract as well. It doesn't give you pictures, it gives you diagrams made of arrows. Of course, not every mathematician would agree with the fact that category theory is the most abstract of all fields of pure mathematics. But first, watch the video and try to open your mind to this possibility. Also, if you're enjoying the video, do not forget to like it and to subscribe to the channel. Let's define a few terms, loosely though. An object is a dot. It has no inner structure. Morphisms are arrows with an origin and a destination. A category is a bunch of dots and arrows with a specific configuration. For example, this is a category of objects O1, O2, and so on up to O7. And morphisms F21, G34, identity 2, and so on. Now, if you're curious to know what the definition of an object is, you'll quickly run into some problems. So let's ask the question, what is the definition of an object in category theory? First of all, many textbooks don't even define it, but you can find something similar to that. An object is an abstract entity that serves as the domain or codomain of morphisms. This is not very clarifying, but for a good reason. Defining an object is an awkward task because of how fundamental it is. I like to illustrate it with an analogy from physics. The analogy is not perfect, okay, but it will do. In nature, we have elementary particles, like the electron. They're called elementary because they have no internal structure. For example, a proton is composed of 3 quarks. A meson is composed of 1 quark and 1 antiquark. These are not elementary particles. They are made of smaller pieces. But if we could zoom in on an electron, you'd still see just a little dot. That's why it's elementary. Objects in category theory behave in a similar way. You can describe what an elementary particle does, how it interacts with other particles or with magnetic or electric fields, but you can't really open it up and look inside of it. A categorical object is just like that. It can only be described by its relationships with other objects. In other words, the web of arrows or morphisms coming in or out of it. Okay, enough of intuition. Time to see a concrete example. First, the category called monoid. Just one object and its identity. This is the only morphism in here. Pretty simple. Second, poset category. There is at most one morphism between 2 objects in this category, so this would not be allowed here. Third, Another example of a poset category would be a category with just three objects, A, B, C, and morphisms F, G, identity of A, identity of B, identity of C, and F composed with G. Every time we have a situation like that, where two morphisms can be composed, their composition always exists. This is part of the definition of a category. Another thing that's part of the definition of a category is that every object always has an identity morphism. Plus, every composition of morphisms is associative in a category. The set of all morphisms F1, F2, and so on up to Fn between two objects A and B in a category C is denoted this way. In a similar way, for all morphisms G1, G2 up to Gm between two other objects C and D in the same category, we write this. These are called home sets for each pair of objects. The term home historically comes from homomorphism, which is a mapping that preserves structure in algebraic settings. We'll explain what a homomorphism is later on, so don't worry about it yet. But actually, not all morphisms are homomorphisms in a category. But the name home set remained as a historical convention. Another important thing to say is that there can be 0, 1, 2, 3, or even infinitely many morphisms between objects. We can go even further. There can be uncountably many morphisms between two objects. There can also be multiple morphisms from one object to itself. Let's see a few examples to illustrate these concepts. First, the category set, where objects are all possible sets and morphisms are all possible functions between them. Let A be the set 1, 2. Then, the home set in the category set of A with itself is this set of functions. These are all possible functions from A to itself. If B is the set banana, apple, orange, then there are 9 possible morphisms from A to B. This is the list of all of them. The home set, then, is expressed this way. All functions from A to B. There are 9 of them. Second, category GRP, where objects are groups and morphisms are homomorphisms between them. Let's recall that a group is a set of elements that represent actions you can do, like rotating a shape or walking back and forth, such that you can combine them or even do nothing. Rigorously speaking, a group is a set G with a binary operation satisfying the following: associativity. It has an identity element, and each one of its elements has an inverse. And what about homomorphisms? Let's start with a simple example. Consider the group of symmetries of an equilateral triangle. This is called the dihedral group, and it's denoted as D3. Each of its elements are actions or moves that you can perform without changing the symmetries of the group. So, for example, this is a valid move. This is not a valid move. The symmetry is not preserved in the second case. There are 2 generators of all possible moves in this group, so any action you can think of is just a combination of these. R, which is a 120-degree clockwise rotation, and F, which is a flip or reflection. It turns out that there is another group that is incredibly similar to this one, and these similarities can be best noticed when drawing their Cayley diagrams. This is the group of symmetries of a list of 3 elements, 1, 2, 3, where the order matters. It's called the symmetric group on 3 elements, S3. Each of its elements is a move or action that you can perform without changing the symmetry of the group. So, without changing the fact that you have 3 different elements listed in a specific order. So, for example, this is a valid move. This is not a valid move. The symmetry is not preserved in the second case. There are 2 generators of all possible moves in this group, so any action you can think of is just a combination of these. R, which is a 3 cycle, and F, a transposition. All of this to say that this intuitive similarity between them can be formalized with the concept of a homomorphism, which is a way of translating moves from one group to another. In our case, there is a homomorphism phi that translates rotations and flips in D3 into 3 cycles and transpositions in S3. Therefore, here's the rigorous definition of a homomorphism. Let G and H be groups with operations dot and star respectively. A group homomorphism, then, is a function phi from G to H such that for all elements A and B in G, this equation holds. In our example before, the homomorphism phi translates moves R and F from D3 to S3. A common confusion for people when learning these things for the very first time is that they look at this equation and may think that dot and star are the moves R, rotation or 3 cycle, and F, flip or transposition, that we've seen before. This is not the case, because the elements of a group are not the thing about which we study all the symmetries. So not the triangle and not the list themselves. The elements of a group are the moves one applies on these things. In the case of D3, the triangle is not an element of D3, but all the possible compositions of actions are. And in the case of S3, the list of 3 elements is not an element of S3, but all the possible compositions of actions are. So, if in this equation the left-hand side represents D3, and the right-hand side represents S3, we then have, for example, that A could be a rotation, B could be a flip, F of A 3 cycle, and F of B a transposition. If you enjoy our videos and you want to support our work, consider becoming a member of the channel. Thanks for that. Going back to the category GRP, all this internal structure of D3 and S3 is ignored under the lens of category theory. And in the diagram representation here, they become just dots, since they are objects with a narrow phi, which is the morphism between them, in this case also a homomorphism. There are of course many other examples of objects, in other words, groups in this category, that are homomorphic to each other. Now, as for the next category, Sophia will be the one to tell you guys about it.
3. Category top. In this category, objects are topological spaces and morphisms are continuous maps between them. Now, this category has a subcategory called top house, which is a category in its own right. It's the category in which the objects are topological spaces that are also Hausdorff. We will not get into the details of topology here, but a Hausdorff space is a topological space where any 2 distinct points can be separated by disjoint open sets. We found out that people can better understand and appreciate the fact that a space is Hausdorff by first understanding what a non-Hausdorff space is. Let's see an example. Imagine 2 copies of the plane R2, say P1 and P2. Now glue them together along every point except the origins. Let's call them 001 and 002. That means all points x and y different from the origins in P1 and in P2 are identified. So in other words, they're the same now, but the origins are not. 001 is still a different point from 002. Now, what happens if we try to separate 001 from 002? We can create 2 open disks, or neighborhoods, one around 001 and another one around 002. The problem is, no matter how small the disks are, they will always share all the same points except the origins, so the disks always overlap. This makes it impossible to separate 001 from 002 with non-overlapping open sets. So the space is not Hausdorff. The morphisms of the category top house connecting Hausdorff spaces are continuous maps, just as the morphisms in top. Literally, the only difference this time is that these morphisms are restricted to associating only objects that are Hausdorff spaces. Interestingly, the category top house has a subcategory as well, called homeo, which abbreviates the word homeomorphism, and is a category of its own. In this category, objects are also Hausdorff topological spaces, like spheres, tori, with genus 1, 2, and up to n, Mobius strips, and so on. Morphisms, though, are homeomorphisms now. Definition. A homeomorphism is a continuous map F between topological spaces X and Y. such that f is bijective, so 1 to 1 and onto, and f inverse is also continuous. Intuitively, a homeomorphism is a way to deform one shape into another by stretching, bending, or twisting, but without tearing, cutting, or gluing, so that the two spaces remain topologically the same. An example of a pair of objects with a morphism connecting them in the category top house, but not in homeo, is the continuous injection f from the Mobius strip to the Klein bottle. So in other words, the Mobius strip can be embedded in the Klein bottle. But f is not surjective. And on top of that, there is no continuous inverse map from the Klein bottle to the Mobius strip. In other words, the Klein bottle is not embeddable into the Mobius strip. Therefore, there is no homeomorphism between them. Another example would be the objects D2, a disk, and S2, the two-sphere. There are many continuous injections from the two-disk to the two-sphere, but none of them are surjective. Likewise, there are many continuous surjections from the two-sphere to the two-disk, but none of them are injective. Therefore, no continuous bijection exists between them whose inverse is also continuous. They are definitely in the category top house, since the disk and the sphere are Hausdorff spaces with many continuous maps between them. But they are not in the category homeo, because there is no homeomorphism between them. Now, let's see examples of pairs of objects with their morphisms in the category top, but not in top house. X is the set with elements A and B with a discrete topology. This set defines all the subsets of X that can be called open. This is clearly a Hausdorff space, since we can separate its elements. Y is the set with elements 1, 2 with a trivial, also known as indiscrete or coarse, topology. This is not Hausdorff because there are no open sets that separate 1 and 2. X and Y are definitely topological spaces, and there are certainly continuous maps between them, like this one. But since Y is not Hausdorff, this pair of objects with morphisms do not belong to top house, even though they do belong to top. Another example is X equals the plane with two origins with the standard topology on R2. This is a non-Hausdorff space. Let Y be R2 with the same usual topology. This space is Hausdorff. Now we can create a continuous map that identifies each pair of points X and Y just as you might have expected, including the origins 001 and 002 in X that are identified to the unique origin 00 in Y. This is a continuous map, but since X is not Hausdorff, the pair of objects with all its possible morphisms belong to the category top, but not to top house. Of course, this representation is not perfect, and you can see how it becomes problematic when we talk about a pair of objects in a morphism from X to Y that belongs to the category C, but not to its subcategory D. And at the same time, the pair of objects in a morphism from X to Z that belong to D. The problem arises when you need to decide where to place the object X. It can't cross categories like that. Should we place X in the C, but not in the D box? The problem is just a reflection of the fact that categories are not sets. They are way more abstract than sets, so don't take these drawings too seriously. Instead of talking about pairs of objects with morphisms connecting them, in category theory, it's preferable to only talk about morphisms belonging to categories. Next, the fourth category, vect over the field of real numbers. This is the category where objects are vector spaces over the field R, and morphisms are linear maps. As you might have guessed, we're now studying the abstract structure of linear algebra, but through the lens of category theory. Let's see some examples. Consider the objects R3 and R, connected by this morphism, x plus y plus z. This is clearly a linear map from one vector space over the field R to another vector space. Now, let M2 by 2 of R represent the vector space of real 2 by 2 matrices. We can, for example, define the following linear transformation. This linear transformation belongs to our category. Another example is the pair of infinitely differentiable real functions and continuous functions on the interval AB on the real line, with the morphism being the derivative map D between them. counterexample would be the nonlinear map f of xy equals x squared y between vector spaces R2 and R2. So we can simplistically think of this category this way.
The last example, the category man. The objects in this category are differentiable, so smooth manifolds, which is equivalent to say that they are topological spaces locally homeomorphic to the Euclidean space Rn that have a smooth structure, so with charts and smooth transition maps. Morphisms are smooth maps, which are infinitely differentiable, or C-infinity functions between manifolds. This is a huge category, by the way. The morphisms don't need to be invertible or bijective, just smooth. There's also the category diff, which is a subcategory of man. Here, objects are smooth manifolds, just as in the man category. Morphisms are diffeomorphisms, which means they are C-infinity maps that are bijective and whose inverse is also smooth. The morphisms now are more strict than before. If you want to be one of the first people to have access to our future books and courses, sign up with your email address on our website. Link in the description. Let's see some concrete examples. The first example is a morphism between two smooth manifolds that relate them using a smooth bijection with smooth inverse. And therefore, this morphism lives in the category diff, but also in man as a consequence. We're defining a diffeomorphism F between the two-sphere, S2, and an ellipsoid, E. But how exactly can we do it? First, we can use stereographic projections for each one of them. These will be global charts, phi and psi, which map every point in each manifold to their own copies of R2, minus a point at infinity. Now we can compose mappings to define F and F inverse. You might be asking yourself right now, why would a person in their right mind complicate their lives that much with all these charts, maps, compositions, just to define F and F inverse? I mean, can't we just associate points from the sphere to the ellipsoid? It would be much easier, right? Well, it turns out that there is a deep reason for it in differential geometry. The functions f and f inverse are maps between curved spaces, so we cannot directly apply the tools from multivariable calculus, like defining derivatives and computing things with them, because usually they are formulated in linear flat spaces, like Rn. And that's why we need all these coordinate charts, phi, phi inverse, psi, psi inverse, and intermediate maps, gamma and gamma inverse, also called transition maps. Since gamma and gamma inverse are maps between flat spaces, we can take their derivatives and talk about them being smooth in the classical calculus sense. Then we define f and f inverse to be smooth if gamma and gamma inverse are smooth. Of course, we could define smooth bijections in a similar way for other pairs of smooth manifolds. Second, the two torus and the two sphere with a constant map. This is the example of a morphism in the category man, but not in diff. We can collapse the entire torus onto a single point on the sphere. Consider the map F with f of t equals x0 for all points t on the torus and some fixed point x0 on the sphere. This map is continuous and smooth. In fact, all its derivatives vanish since it's constant. Therefore, it's a valid morphism in the category man. However, it's not a diffeomorphism because it is not bijective. As a result, it doesn't belong to diff. Third, the two torus and the two sphere again, but this time with polar collapse map. This map sends points from the torus into the sphere. It's smooth and continuous, so it defines a morphism in man. However, it's not injective. The two entire phi circles at theta equals 0 and theta equals pi are both collapsed to the north and south poles of the sphere. Since this map is not a bijection, it is not a diffeomorphism either, and therefore not a morphism in diff. Great! After this marathon of examples and intuitive explanations, we're finally ready to see the rigorous definition of a category. Definition: a category C consists of, first, objects, which are collections of entities denoted as A, B, C, and so on. Second, morphisms. For every pair of objects A and B, a set of morphisms, also called arrows, can be defined and denoted as home set in the category C of A and B. Each morphism F in this home set is written as F from A to B. Third, composition law. For any three objects A, B, C, and morphisms F from A to B and G from B to C, there is a composition from A to C such that this composition is a binary operation on morphisms. Fourth, identity morphisms. For every object A, there is an identity morphism from A to itself, such that for every F from A to B and G from C to A, these relations hold. And fifth, associativity. For morphisms F, G, and H, we require that this composition always exists. If you want to take a closer look at everything we saw in this video, check out the PDF link in the description. A category, therefore, is a context where we can compose maps, and these compositions behave just as in set theory or algebra. They are associative and they have identity elements. The examples of categories we've seen were set, GRP, top and its subcategories, vect over the field R, man and its subcategory diff. Now, let's point out something very interesting. If we take sets and give them some extra structure, we can turn them into groups. So I guess we can represent it with an arrow coming out of the category set and landing on GRP. We can also add another collection of extra structure to those sets and then turn them into real vector spaces. Let's represent it with an arrow connecting the category set and vect over R. Also, each category should be connected to their subcategories through an inclusion arrow. What about identity arrows? I guess we can do that. We can also create some sort of forgetful arrow that, instead of adding structure, forgets it. We could produce many other arrows that logically connect these categories. You know, this is getting way too clustered and messy. In order to better visualize what's going on here, why don't we collapse each category to a point and ignore their internal structure just for a moment? I hope by now you get where I'm heading to. Each of these categories can themselves be viewed as objects inside a larger structure called cat, which is the category of categories. The morphisms between these objects are called functors, and they are not just arrows we make up as we feel like. These are mappings between categories that preserve their internal structure. They map objects to objects, morphisms to morphisms, and all of this in a way that represents composition and identities.
This particular perspective opens a door to a whole new level of abstraction. Instead of just studying structures within a specific category, we can study the relationships between entire mathematical fields. If you want to learn how to study math effectively, check out this 4-step guide. See you guys there.